Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to connect mathematics to current events and daily life using newspaper articles and TI technology. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts for all my students. So I'm excited to be joined by our panelist, Ron Lancaster. Ron is an associate professor at the University of Toronto, where he teaches mathematics courses for pre-service, middle, and high school teachers. Ron's professional activities include consultations and conference presentations around the world. He is the recipient of the 2015 Margaret Sinclair Memorial Award, recognizing innovation and excellence in mathematics education, awarded by the Fields Institute. Ron, it's great to have you with us tonight.
Hey, thanks a lot, Mike. Looking forward to it.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions that you have for Ron using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event's certificate of attendance at the conclusion of the event. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. So tonight we're obviously moving through some welcome and introductions. The meat and potatoes of what Ron's going to be talking about tonight is going to be connecting mathematics with the real world, which is, I think, a pretty important concept that we all try and strive for in our mathematics classrooms. And stick around to the end because we're going to be giving away to one lucky winner a T-Cubed International Conference registration. All right, Ron, I am giving you control. Feel free to share your screen.
Okay, Mike. Can you see it?
Yep, looks good.
Fantastic. Well, look, welcome everybody. I know this is a busy time of the year. For some of you, school is just starting, and for others, you've been teaching probably for a month. But what I'd like to do tonight is just add to the good things that you're already doing in the classroom. And, take some current events, articles from the newspaper, and incorporate them into the classroom. The mathematics is going to be fairly simple tonight. It'll be at the middle school, high school level, but even if you teach below that, there'll still be things here for you. I mean, it's the spirit of what I'm doing that I think you'll get out of this. So, by the way, if you do teach high school, you might notice my email address, ron2718. That 2718 is deliberate. It's the beginning of the number E. And that's why I have the 2718, because I wanted an email address. Anyway, and my license plate is DYDX, so I wear mathematics on my sleeve. So this is a picture of me. This is a bit unusual for me because usually I do face-to-face PD, and I get to see everybody, and you get to see me. But that's a picture of me that was taken in Hong Kong this summer. I was there in July. If you're wondering why there's an infinity symbol there, the coffee shop I was in was called 01. How cool is that? They actually joined the 2 zeros to get an infinity symbol. So, and they have good coffee too. So, look, back in 1994, I created a column for the NCTM called Media Clips. I had a co-editor at the beginning, Charlie Marion, and this column actually ran until May 2017. And if you join the NCTM, or if you're already a member, you'll actually have complete access to the entire set of columns. And every one of these columns was about taking newspaper articles and articles from the media and having math questions with solutions. So there's a gold mine here waiting for you of material. One of the things that I wanted to do right now, just for a moment, is just to get all of us thinking about why would we use a newspaper in a mathematics classroom. I mean, if I had all of you with me, I think I'd have a discussion about this for about 5 minutes and get some responses from you. but that's not really easy to do here. So here's my top three. Relevancy, I think that's a huge issue. Mike referred to that at the beginning. Critical reading and citizenship. When I think of relevancy, this is an article out of Edutopia, and what David Weiss is trying to do here is to talk about that, we're not covering the curriculum. We're trying to view the world through the lens of mathematics. And he's speaking about relevancy here and engaging students. When I think of critical reading, this is a huge issue. Not having people just look at some text and just accept it and move on, but examining what's there. Jennifer Duncan from the University of Toronto wrote this piece. This is actually part of a bigger article, but I thought that she really nailed, this idea of thinking critically. You analyze, you interpret, you evaluate. So that's another reason for using newspapers. And I think the final big one for me is citizenship. I think it's really important that, as citizens, we are connected, that we know what's going on, and that we can understand what's happening. We're informed. So for me anyway, that's my three big issues of using a newspaper in a classroom. There's others as well, and you might have your own as well. You can maybe add those to the chat. So, I was in Hong Kong, as I mentioned, in July of this year. And when I left, there was actually a protest at the airport. And I was up on the departure area, and I was looking down at the arrivals area, and that's what I could see. These protesters were invited to the airport by the airport workers. And it was very peaceful. They were chanting. I didn't see any evidence of any police. But as I say, it was quite quiet. It was peaceful, and it wasn't rowdy. But when I came home, I looked at the Globe and Mail newspaper, and my print version, the headline said that protesters stormed the airport. And I was set to send the newspaper my pictures and a letter to the editor. And then I looked online, and they actually changed the story. And I think what probably happened is that they had more information, and they modified it. And this time they talked about people, converging at the airport. There's quite a difference between that. But what really caught my eye was the note about how many people were there. So the organizers said that, about 15,000 people took part in the protest over the course of 11 hours. And then they say, wow, police put the figure at 4,000. The way this is written, it's almost, they're opposing each other, these two numbers. And this is a great opportunity for students to actually read this and figure out what's really being said. Are two different things being said here? I'll let you think about this, but for me, when I see the 15,000 people, that, the organizers aren't saying that there were 15,000 people there at once. It was over the course of the time. So these two figures here could actually be in harmony. If you do some searching online about the protests, you will find wild variation, though, in the reported figures for the number of protesters. Some newspaper articles will tell you that there were 1 million people. And then, that's according to the organizers of the protest. And then later in the article, you'll find that it says that the government said that there were 10,000 people there. And then they also quote the police saying how many there were. And that can be tricky because if, the police are siding with the protesters or with the government, the figure they quote might be, variable as well. So this really leads to the point about how would you count the number of people in a crowd, and why would this be important? I mean, who would care about this? So let's do a field trip. I just want to take you to downtown Toronto. I've been creating math trails for my students downtown since the mid-1990s. And one of the things I have my students do year after year after year is visit this fountain. And this is a huge area in between big buildings. And I ask students to, imagine that there is a concert that's going to be held here, and that you're in charge of determining how many people could stand comfortably within the area. And the students have to, first of all, estimate it, and then develop an action plan for coming up with it. This is actually a picture of a model of this area, so you can see the fountain there, and there's a better picture. And it's really interesting watching my students do this problem because there's all sorts of assumptions that they make. You can do this with your students. Just get a whole bunch of students and have them stand inside a rectangle, get the area of that rectangle, and count how many people are in there. Maybe have different groups do this and then come up with an average and do it. But anyway, that's what I was particularly intrigued with the protests, was the number of people that were there. So let's take a look at our first example, where I'm going to use some TI technology as well. So this is a bit of a quirky article. This is also from the Globe and Mail. But here's this woman. She is going to Home Depot. And so, she's telling this story about how she's in here. And she buys some house numbers. So she buys a 5, a 4, and a 1. And she discovers that these are the wrong size. And she's kind of wondering, like, how could they be the wrong size? I mean, you can see the bottom there. She says, really? They have rules about this? Well, it turns out that in Toronto, there actually is regulation about the size of your house numbers. This may seem really bizarre to you, and you might think this is really crazy. I mean, is this all the city have to do with their time, is just kind of make these regulations? But here's the issue. There's actually been cases throughout North America where the fire department has showed up somewhere and they can't read the house number. Here they are showing up and they thought that it was 710, so they're, going into the house there to put out the fire when the fire is really at 716. This is actually from a card, that image. So I looked up the city code to find out what it is, and here it is. So there's a thing called the maximum setback from the curb. So that's from your, from the curb to your business or from the curb to your house. This data here is actually for residential properties. And you can see that if the maximum setback is 15 meters, your minimum size for your house numbers is 10 centimeters. And they also give the numbers here in non-metric units as well. So take a look at this data. What do you notice? What are you wondering about? What questions do you have? So when I do this with my students, here's what often happens. Students will look at, say, the metric column, and they'll notice that they're going up by 15, except for this 22.5. I mean, that's kind of just inserted in there. It seems kind of strange. Without that one, you have this 15, 30, 45, 60. And in the centimeter column, you have things going up by 5 and 10. And, going up by 5 is because of that 22.5. And, you might be wondering, why were these numbers chosen? Did somebody do a study to see whether these are quite visible? Is that how you would do this? So if your students were in charge of setting up the minimum number size, what numbers would they pick? So you might be wondering about that. And, the questions you might have is, what's the relationship here? What kind of formula could you have here between this data? One of the things that I hope you've noticed is that there's a 10 here and a 20 and a 40. That's being doubled every time. So when you go from 15 to 30 to 60, that's also being doubled. So these are the X values here. So the value of X is being doubled, and same with the value of Y. I smell a linear function here. So anyway, we can let X and Y represent these quantities, and we can find a mathematical model. And because we kind of sense that there's going to be, some sort of linear relationship here, we can go to our calculator and actually do it. So in order to make this a little bit easier on myself here, what I've done is I've set up a program here so that I have all of the data inside. So it's actually in this program number 5. So I'll just put this in. And what I've done is I've loaded in that data. And I've also loaded in the equations and all of that information. So there's the graphs. And I could turn on the scatter plot as well so that you could see that. But this is the data here for this. So I'll just run the program, program 2. So we'll run this here. And you can see the equations here for this. And it's an interesting thing to ask, what do these equations represent? So if we go back to the PowerPoint here and look at it, there's two sets of data here. There's the meters and the centimeters and the yards and the inches. What you might want to do with your students is just ask them to find a mathematical model for y in terms of x and let them decide, what to use, whether it's either the metric or the non-metric to do that. And then you can use your equation to actually calculate the minimum number size. So you could do that by looking at the graph, you could use a table, or you could use a solver, or you could solve an algebraic equation, to do that. So, by the way, here's a beautiful puzzle about house numbers. So you can take a look at this later on, but this is one of my favorite puzzles. So you live on a street, and you don't know how many numbers there are on your street. But what you've noticed is that if you take your address and if you take all the house numbers less than your address, it's the same as the sum of all the house numbers greater than your address. And the question is, what is your address? And how many houses are there on the road if my house number is in the 30s? That little piece at the end helps you narrow it down. So, this is kind of one of these questions where anybody can really start this, because you could just try 30, 31, 32, 33, 34 and kind of work with it. If you delete that second part of it, it becomes a harder problem because you don't know where to start. But it's a really cool problem. So here's a second example for you. This one is also a little bit quirky. So this is an article that I also found in the Globe and Mail. I just happened to have used this newspaper here. And they were reporting on this math contest that happened with students. And this article happened to focus on this particular math problem. So you have 200 fish in an aquarium. 99% of them are guppies. The question is, how many guppies must be removed to reduce the tank's guppy population to 98%? So when I've used this with students, intuitively, most students think that you don't have to take out very many guppies, because all you're trying to do is go from 99% to 98%. Not very much. It turns out in this article, they mentioned the student who knew the answer to it, and, he won the contest and blah, blah, blah. So this is a really cool problem. So what you can do is ask students that question. How many would you, maybe even just make a guess. What do you think the answer is going to be? And then set up some algebra for this. So you could let y be the percentage of guppies in the aquarium after X guppies have been removed. Good question to ask are, what are the restrictions on X? Like, could you remove 500 guppies? No. Could you remove minus 10 guppies? No. And then determine an equation for this, and then make a graph. And you notice in part C that I've telegraphed what the domain is. And you might want to leave that out. You might leave it up to your students to figure out what the domain is and let them figure it out. And then there's a piece where you describe how the value of y, that's the percentage, changes from x equals 0 all the way up to x equals 198. And further questions you could ask is, how many guppies must be removed to reduce the tank's population to, say, 50%? So let's once again take a look at some TI technology here. So I'm just going to get a few things turned off here. So if you just bear with me. So, okay, we'll get the plots turned off, and we'll clear out these equations. Okay, And we'll also clear out any data here as well. Okay, so here goes. So again, I have a program, and if there's time afterwards, I can show you what I've done here in order to do this. So this is just loading in the window. It's loading in the equation. And this way, I don't have to bother doing this in front of you. You might find this convenient in your classes as well. So there's the equation. So, you know, you've got 198 minus x, because don't forget, 99% of the fish are guppies. So that's 198. You're removing x, and it's all relative to how many fish there were at the beginning, 200 minus x. So this is a beautiful rational function here. And of course, you multiply it by 100. This is really just the ratio of two linear functions. That's all it is. And so you could ask students to go to a table. They could take a look at a table, and they could try to find out, when is it 98% and not 99? So if we take a look at the table here, one of the things you're going to be struck by is how slowly it changes. Now, you know, for math teachers that maybe teach at the high school level, perhaps the solution of this problem and all of this is kind of obvious. But I found for younger students in middle school and early high school, it's not obvious that this happens, but this is incredibly slow. You can go way, way down, and it's just changing very slowly. So that initial thought that you're going to have to, you know, remove just a few fish to have 98% guppies isn't true. You're going to have to remove a lot of them. And if you take a look at the graph, whoa, that thing just goes along way up at the top there, and then it just drops like a rock. So if you want the 98%, it's going to be a really big number that you're going to have to remove. So you could have students take this equation and set it equal to 98, or students could use some guess and check to figure it out. You could also use the solver. So on the TID4, you have this numeric solver that you can use. And you'll see here that I've got this set up here so that I have y1 minus y8. And then when I actually solve here to come up with the answer, So anyway, I won't come back to that. There must be something in here that I've set up incorrectly here. Let me just see if I can just figure this out here with this. So, okay, what's up here? Anyway, I'm not sure. But anyway, you can use the solver to do it and to work it out. And it may surprise you that the answer is actually 100, right? Because 198 are guppies. If you remove 100, you've now got 100 fish left, and 98 of them are guppies. To get 50%, you really have to remove also quite a few, to get down to 50%. So that's a nice problem. I mean, it's kind of a quirky thing about this math contest, but the mathematical content is quite nice. So here's our third example. So I was in Abu Dhabi a number of times. I've done some consultant work for the American Community School. And I was there March 15th, 2015. And I was sitting outside having dinner at the Intercontinental Hotel. I was having dinner. And I was looking at the Etihad Towers. They were actually just being finished here. So these are the towers here. They're actually beautiful towers. The architecture in Abu Dhabi is absolutely stunning. I've been also in Dubai a number of times and Qatar as well. And incredible, the buildings. There's actually a building that's in the shape of a coin. It's actually round. That is amazing in Abu Dhabi. Anyway, I'm sitting there reading the newspaper. I'm looking at the national newspaper. And I came across this article that actually left me speechless. It was about a movie called The Fast and Furious. I hadn't seen the film, but this article was talking about it and how it was based around these Etihad towers. The reason I was left speechless is because here's what I was looking at. There was this 2-page spread with all of this information about the movie and this graphic. I was just stunned. I mean, this just spoke to me mathematically. If you just take a look at this for a few moments, you'll see that there's just all sorts of things. In the upper right corner, you'll notice that the top speed of this car, it's insane, 385 kilometers per hour. And you can reach 100 kilometers per hour in just under 3 seconds. An interesting question is, how far would it take for that car to stop driving at 100 kilometers an hour or 385 kilometers per hour? But anyway, there's all sorts of mathematics in this graphic, and you must come back to this later on and take a look at it. The 32 degrees down here, where is that from? How would you work out the 32 degrees? What about all of these other figures here? What about this equation? S equals ut plus 1/2 at squared. That's the standard equation from physics for this kind of motion. But, where are the numbers coming from? So you could provide your students with this graphic and ask them to be the fact checker. So let's say that they work for the national newspaper. And they've been presented with this graphic, and it's their job to go through this and check everything. So they've got to go over every little detail here and check all the numbers. What would they do? What would be the mathematics that they would do for this? So I hope you get some mileage out of using this. I found that with younger students, this is connected with them because it's a movie that many of them have seen or they're interested in, these Fast and Furious movies. To be honest with you, this is not a film that I would go see. I was just at the Toronto National Film Festival this past weekend and saw 8 films, and they were all, kind of international art films that I saw. And, Fast and Furious isn't actually on my list. However, I have made an exception for this movie. I just had to go see this. By the way, just a backdrop on this in case you're wondering if you haven't seen the film. What actually happens in this movie, I know this is crazy, but there is a car up in this building, and there's a chase scene. And the car actually crashes out of this building, crashes into a building beside it, passes through the building, and crashes into the building beside it. And then it stops. If you're wondering, why is the car up there? What's the chase scene? Well, go see the movie. But anyway, there are some reasons for this, but I won't spill the beans on what it is. So anyway, that's something that I hope that you'll be able to use. So let's take a look at some mathematics related to that story. So here's a newspaper article out of the local newspaper here. This is absolutely crazy. This is out of the Hamilton Spectator. There is a team that was driving, if you can imagine, 254 kilometers on a highway outside of Toronto. The speed limit is 100 kilometers an hour. Absolutely crazy. Well, needless to say, this 19-year-old was charged. In Ontario, we have a charge called stunt driving. And if you are 50 kilometers over the speed limit, the police can take your car, they can take your license for 7 days. I know some of you may be surprised at this because, the person is actually being considered guilty. But this has been contested in the courts. Nobody has won. They're only taking it for 7 days. There's a court hearing that goes to court, and that's it. I think the thinking of the police here and the government is that anybody doing this, they need to be taken off the road. There's huge charges for this. You lose points, and the fine is unbelievable. There's actually been a number of young students, 19, 18 years old, driving, who have had the car taken, and it turns out that it was the parents' car. You can imagine the conversation, that goes on at home about this. This is a really important example to use with your students. So one of the first things that I would ask you to do, or suggest that you do, is find out what happens in the area you live in. So is there a similar kind of law? So if you're pulled over for doing 80 miles an hour over the speed limit, I mean, obviously you get a ticket, but what happens? Are you allowed to get back into your car and just continue to drive, assuming that you're not drunk? So first of all, find out that. And here is some mathematics. By the way, I have all kinds of articles on this. You can see that this is a collection. And by the way, breaking news, if I can just break out of this for a second. Here's some breaking news from today. So it's September 10th. A driver's clocked at 100 kilometers an hour over the speed limit. So this is crazy. So once again, he's been charged. And you can see here that the fine, it ranges between $2,000 and $10,000. And you could also be put in jail for 6 months. And, if you're caught doing this twice, it's jail sentences and all of that. But so anyway, it just happened today. So there's a great website that you can go to. There's actually a number of them, but this is my favorite. When you go to this website, you can actually enter in the conditions of the road. You can enter in the units, so either miles per hour or kilometers per hour, your choice. And then you can do one of two things. You can put in the stopping distance. That's something that the police might be interested in because they might be measuring skid marks. And so they've measured a skid mark and they're trying to get some sense for how fast that car was driving before an accident. But you can also enter in an initial speed. So what you could do is have your students go to this website and then take this chart. Sorry, I'll just back up, sorry. Take this chart and complete it. And you might want to use, if you're in the US, miles per hour. So I've used kilometers an hour here. But you can, enter all these numbers in and get the data. Now the question for your students is, what type of relationship here? What do you have? So you could ask your students, first of all, look at the data. What do you notice? What are you wondering about? What questions do you have? One of the things that I hope you notice is that this doesn't look like linear data. So if you do the first differences here and work them out, it sure doesn't look like linear data. So that would be a good starting point for your students to actually work out the data, the differences for this. And, so is the data linear or nonlinear? So if you do the second differences, you'll actually find that it's constant. So that's telling us that it sure appears that there is some quadratic data here. Then you can have students graph the data. And you can ask your students if the graph, supports your answer above. I've actually meant part A there, it's a typo. So does the graph support that? Great question for your students is, if you double your speed, will your braking distance also double? I found that when I ask people this, most people say yes. Turns out it's not. And you can also ask other questions, like give the students an article like this. And what is the braking distance? This is an interesting article here because if that's all the information you have, you don't know what the speed limit is. And so, you don't know what the driver was driving here. So you'd actually have to visit the website to find more information. And you can do the same thing, but this time finding an equation for this. And you can do it for wet asphalt. You can do it for ice. You can take all sorts of road conditions for this. Find the equations, compare the equations, and answer a lot of questions. So let's take a look at some TI technology using this. So again, I'll just turn off the stat plot here. So, so just get this here, turn the plots off, go to the equations, get rid of the guppies here, and also get rid of the data that's here. Okay, and here comes the equation. So I've actually got a bunch of programs set up here, but let's take a look at the braking on a dry road. So we'll open this one up. What's actually happened here is the calculator program has taken the data and put it into the list editor. So that's the data that you were just looking at here. And of course, what I can do is turn on the plot and actually take a look at the graph. And this also, put in the quadratic regression as well, and put that in. But this will be a nice exercise for your students, having them walk through, looking at the data. What do you notice? What are you wondering about? What questions do you have? What type of data it is? And then actually finding the equation for it. Now, if you go through and do this for the other road conditions, it's actually really interesting to compare these equations. The coefficient of x squared, how does that change when you're on ice or on a wet road? And what about the coefficient of x? How does that change? Actually, you'll notice here that the coefficient of x is pretty tiny. Kind of looks like it's essentially 0. And same thing with the constant term here. You talk to a physics teacher, they're going to tell you that the braking distance is actually, kx squared. That's the equation. So there is no x term, there's no constant term. In fact, that's something that you might want to do, is invite a science teacher into your class and have them talk to your students about, why is this true? Like, why is it that the braking distance is a quadratic function of the speed? And have them do, a 5 or 10 minute lesson on why that is the case. That would be a nice thing, I think, for you to do and work that through. So here's another example. By the way, just a quick field trip here. So I'm going to take you back to Abu Dhabi before we look at our next example. I'm going to take you to the 74th floor of one of those towers. So here we are. We're looking down at those buildings. And I'm standing at the observation deck. And you notice there's a 300 there. Interesting question for your students is, what does the 300 mean? So you might want to show them these pictures. Is it 300 feet? Is it 300 meters? What is it? And have them think about this. And here's a mathematical question for you. When you look out the window, as I did, from the 74th floor, and if you've got a clear day, how far can you see? How far to the horizon can you see? So on a clear day, how far can you see? There's a certain age thing that's going to happen here. If you're a certain age, that may ring a bell. On a clear day, how far can you see? This is not the answer. It's not forever. No. And this isn't the answer either. It's not miles. It is true that you can see for miles, but both of these answers are not specific enough. So it turns out that a number of years ago, the Globe and Mail had a column called Ask a Journalist. And somebody wrote in and said, why do tall guys find it easier to get dates than us normal-sized guys? And this journalist wrote back and said, well, it's because the tall guys can see farther. And he goes on to say that there's actually a simple formula that you can use to calculate the distance to the horizon. So this physicist, the journalist must have called this physicist to ask him. So Robert Matthews says, multiply your height in meters by 10, add on a third to the result, and take the square root. And he gives an example. So take a moment and think about what the equation is. Multiply your height by 10. So, take your height and multiply by 10. Add on a third to the result, and take the square root. So have you got something in mind? I don't know whether it's obvious to you or not. This is ambiguous. If you give this to your students, some of them may find that they're not quite sure what Robert Matthews is saying. He says to add on a third. Is that like 1/3? Like, what does he mean? So if you let y be the distance to the horizon and x is your height, which one of these equations is Matthew referring to? There's two different equations here. So which one is he thinking of? And the way your students can figure out which one it is by taking the data that he gave. So he says that a 6-footer can see 4.939 kilometers. By the way, you might find it interesting, the mix of the non-metric units with the metric units. And this is in a Canadian paper. It turns out that we did go metric a number of years ago, but you'll still see a lot of non-metric units here in Canada, tons of them. If you were to come and ask some of my students, how tall are you? They would probably respond to you in non-metric units. And, how much do they weigh? They probably respond in pounds. But if you take a room and say, how long is this room? They'll respond in meters. It seems to be things that are personal that we're still using non-metric units. So anyway, it turns out that's the equation that Matthews was thinking of. So 10x plus 10x over 3, so he was thinking of a third of that. That's the equation. And what you can now do is start to ask your students all sorts of questions. You can get out your graphing calculator, you can use Inspire, you can use a TI-84, you can graph this. If you're, at a certain height, how far can you see? If you can see 30 kilometers, how high are you? You can have students graph this and look at what happens when x goes up. So when you change the value of x from 50 to 60 to 70 to 80 and so on, how does the value of y change? You can do the first and second differences. Neither one of those will be quadratic or linear. Neither one of those will be constant, sorry. So this isn't a linear function. It's not a quadratic function. It's something else. So there's a number of questions here that you can use, and you can use your graphing calculator to support that. By the way, I have an interesting question here, just a little aside here for a moment for you. So that's the equation. So you plug in the value of x is in meters. The value of y is in kilometers. Here's a question for all of you. How is it that you can plug in for x something that is in meters and get an answer of kilometers? Like that just makes no sense at all. How can that happen? Because you're taking the square root. If you do the 10x plus 10x over 3, the units are going to be meters. Because, x is in meters. If you take the square root of that, you got the square root of meters. That's not kilometers. So that's a great question for all of you. Some of you, if you have a science background, will know the answer right away. But for others, you might be kind of wondering, yeah, why is it true? So, you can go talk to a science teacher and ask them. What I do want to show you just briefly here is a article from the math teacher. So I also created another column for the NCTM called the Mathematical Lens. And this column is now finished. So it ended in May 2017. This column, it was a nice opportunity for me to say goodbye to the readers. I wanted people to know that they had a license to do math, a bit of a bad pun, and they had a full tank of resources. And it began with my license plate, and there's Fred Hornehau's license plate as well, his dy by dx. The reason I'm showing this to you is there was a photograph that I used right here. And you'll see here that the price of gasoline at this time, near where I live, was $1 a liter. And I like to ask my students, what's the equation? If you buy X liters, how much will it cost you? So if you buy 1 liter, it costs you $1. You buy 10 liters, it costs you $10. And I found that all of my students tell me that it's Y equals X. Makes sense, right? Well, now I ask them, how is it that you can substitute in for X liters and get dollars? That just makes no sense whatsoever. So the question that I posed in this column was this very one. Explain what's going on. And essentially the problem here is that it's really Y equals 1X. The 1 is dollars per liter. And so when you have Y equals 1X, the liters cancel and you're left with dollars. This raises an interesting question. In our math courses, should we write things like Y equals X? Is that okay? Or should we write it as Y equals 1X? What should we do? So anyway, that's something for you to think about and see. So anyway, that's the Ask a Journalist question, or that particular one for that. Sorry, I've just got myself out of order here with this. So I'm just going to scroll ahead here. Sorry about this. And I'll come back to where I was at here. So that was a little aside here about the units here with this equation. So it turns out if you look at the development of this, and there's places you can go online to see it, you'll start to understand how this works. That 10 has units. That's how it's possible to go from your meters to your kilometers. So I'll let you fiddle with that. By the way, Robert Matthews could have just said when he was interviewed, just take 3.65, multiply it by the square root of your height, and that's it. He easily could have just said that. And this is another good question for your students, is to simplify the original formula and come up with 3.65 times the square root of X. And now you can ask all sorts of questions, as I mentioned before about this. From what height could you see 10 kilometers and so on. And you can also give them a newspaper article where, these people are on top of a great big ride. And this newspaper article talks about how far they can see. And you can do some mathematics with this as well. So here's one last article for you. So this is another one of these columns from the Globe and Mail. So this person says, if you're standing at a beach and looking out to the sea in a clear day, how far can you see? Take a look at the answer this time. So this time, the journalist says 1.17 times the square root of the height. Now it's in feet. So now you've got two different equations. So if you go to your graphing calculator and graph both of these, and if you look at them, is that okay? Because now the value of X, they're different units. So could you take the top equation, change the units, and get the bottom equation? And that'll be some fantastic mathematics for you to do with this. So there's quite a few things that you can do with this formula. By the way, the thing that you really want to do with this is make sure you ask students at a particular grade where the equation comes from. So that original equation that you saw way back here. So where do you get this from? And the geometry is really beautiful. You need to draw a circle. You need to draw a tangent to the horizon. And then there's going to be different mathematics that you're going to do with that. You can also look online. Just Google distance to horizon, and you'll find all kinds of things that you'll find there. So there'll be quite a bit of stuff that you'll have there. And this last one is just some homework for you. There has been a lot of newspapers across North America that are trying to save money because they're having difficult times. And our newspaper here in the city has actually trimmed the size of the paper. So they've taken 2.5 inches off the bottom and 1.5 inches off the side. And this person wrote in to the newspaper, it was a letter to the editor, and he says that it's about 10 to 15% less in size. So here's a question for you and your students. What's the size of the newspaper? Can you figure that out from this information? And I'll leave you with that. By the way, this is all going to be available, the presentation. You'll have this at the TI website. But if you want, you can also go to RL, my initials, Ron Lancaster, 2019. It's September 10th, 0910, and TI for Texas Instruments. And you'll be able to download that. I'm going to turn things over to Mike in a moment, but I did want to just close by just taking a look at the graphing calculator. And if you're curious what was going on with those equations, so I'm just going to go into the house numbers one. So I'll just pop this one open and take a look at it. All that I did in the program is I just typed in the data. And I did store in list 1. The store key is down in the lower left corner. I just did that for list 1, list 2, list 3, list 4. I worked out the regression, and then I typed it in. Actually, I did a recall, but you could just type it in. And I did that for Y1 and Y2. And then I set up the scatter plots. And this way, when I run the program, the list editor gets populated with the data. So list 1, list 2 gets filled up, same as list 4. The equation goes up into the Y, the Y equals editor, and the scatter plot is all set up. This is something that you might want to do, in class, because this way you're not entering all the data in front of your class. It's all preloaded. And so that's the program. If you're wondering what was going on with the group stuff that I was doing, what I did is I set up a group. And I grouped together the lists, L1, L2, L3, the equations, and the window. And I put all those together. And then I ungrouped those things. And that's also a nice thing to do, because that way the window gets set up automatically as well. These group files used to be used a lot many, many years ago. I don't see people using these as much, and I find them really helpful. If you want to just quickly see how to do a group, let me just call it A. And I always use number 2, all minus, because when I make a group, this allows me to pick from everything. So I could say I'd like to have the guppy in the group. I'd also like list 1. I'd also like list 2. And then I can scroll down and I can say, oh, something, I'd also like to recall the window that's in place. And I can choose what I want. I can scroll over to done, click on enter, and it's finished. And then when I ungroup that group file, all of those things come back into the calculator. I like using the group files as well, because by accident, if I happen to erase the RAM on my calculator, I mean, you have to kind of try to do it, but I've done it before in class. I've been trying to show students how to do it, and then I've accidentally erased everything on the calculator. Well, because I have those group files, it's not a big deal. I can just bring them back, because the group files are actually in the archive memory, so they're not in the RAM. So that's really cool, and it's a really nice thing to use. So Michael, I haven't had a chance to take a look at the chat room. Are there any questions that have come up that you see?
I didn't see any scrolling through, but I know we do have a few minutes before we finish up, so if anyone does have any last-minute questions, now would be a great time to get those asked.
Absolutely. And, one thing for all of you that I do want you to know is you're more than welcome to contact me. So, if you, for example, start to do some things with some of these data and these activities, I would love to see what you've done. What does it look like in your hands? You've got my email address RON2718 @nas.net. I'm not working with students right now. I am, but I'm working with adult students. So I'm not in the classroom right now, but I'm on a journey to become a better teacher. And whenever I work with teachers, I always ask them, please get in touch with me and tell me, what does it look like in your hands? And that way I can learn from you. I can see that maybe you changed the wording and you've come up with a better way of wording the questions. Or you've asked a question that I never thought of asking. And so that would really help me, and I'd certainly appreciate that. Because as I say, I'm on a journey to become a better teacher, and feedback from teachers is really important to me. Anyway, thanks for tuning in tonight. I hope there's been something here for you, and that you'll be able to make use of some of the materials, and that you start reading the newspaper with your students. Thanks a lot.
Ron, thanks so much. Just a couple housekeeping things as we wrap things up tonight. As I mentioned earlier, we're excited that the T-Cubed International Conference is coming to Dallas mid-March, and it's a great way to meet people like Ron and myself and other fellow educators that are really passionate about teaching and education, specifically mathematics and science, but also technology as well. So we hope you'll join us at the T-Cubed International Conference. And we also mentioned that tonight one lucky winner is going to receive a T-Cubed International Conference registration. And tonight's lucky winner is Gary Brown. So Gary, congratulations. We hope to see you at the conference as well as everyone else. And Gary will be reaching out to you in a couple of days over email to give you a little more information. We currently have a extra credit contest. Information can be found on our website, education.ti.com. And this is the way that you can participate in various activities. All these activities that you would participate in will get you into a drawing to win possible TI technology, T-shirts, and other things. And so, for instance, participating in the webinar tonight is one way that you can earn entries in the drawings, and so you'll need a keyword from tonight, and tonight's code is real world. That's all one word, and it's not case sensitive. So I'm going to type that into the chat window in case you want to check that out. Real world is the, again, code for tonight for the extra credit contest available on our website. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, so we really hope you'll share your thoughts.
Michael, I just wanted to say before we go, I'll be at the NCTM Regional in Boston and the Centennial meeting next year in Chicago. Would love to meet any of you if you're there. And I also plan on being at the Phillips Exeter Academy Math Conference next June, and the Mathematical Sciences Institute in New Orleans next June as well. And we'd love to meet you.
Thanks so much, Ron. To receive a certificate of attendance for tonight, go ahead and click that link that just posted in the chat window. Also listed is a link for the documents that Ron used tonight. If those links aren't working for you for any reason, just hang tight. You'll automatically get a follow-up email within a couple days, and in that follow-up email, you should get links to the certificate, links for the documents, and links to the recording as well. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. Ron, thanks so much for everything you shared tonight and really making me think about, again, bringing that newspaper into my classroom. I appreciate it.
Oh, you're very welcome, Mike. And sorry, I had a few problems using the calculator. My mouse was kind of acting up, and a few little things happened here and there, but I hope it was okay.
Thanks so much, everyone, for joining us, and we hope to see you back online real soon. Have a great night.
Good night, everybody.